Alright, so we're in section 9.1. So the first part of chapter 9 is all about conic sections. And the reason that we call these conic sections, we'll study several different conic sections, is because all of these shapes, let me grab a picture here. That's the one I want. All of these shapes are slices out of cones. So a parabola is a section of a cone when we cut parallel to one of the sides of the cone. A circle is when we cut perpendicular to the axis of the cone, we get a circle. An ellipse is when we cut it at a slant to the axis. And we get a hyperbola when we cut so it goes through both sides of the cone. Equation, the way that the cones work out is the equation, you always get two pieces. You get a lower part and an upper part. So all of these curves, all of these shapes that we've talked about, we've talked a little bit about parabolas, and we know a little bit about circles. You probably worked with circles or ellipses and hyperbolas before. But all of these are conic sections. They're parts of a cone. And the reason that we study them together, we do them a little bit differently. We talk about parabolas a little bit differently than we have before. This is a little more general way of thinking about these shapes. And anytime in math and in science when you can bring everything into one group, so rather than thinking about all of these types of curves as separate things, if we can think of them as part of one bigger thing, that helps us to find out more things about them. So we're going to look at these curves as conic sections, and that'll allow us to work with them a little bit. So today we're going to talk about a circle. The line that gets traced when we cut a cone perpendicular to its axis. So let me write up the kind of a technical definition of a cone or of a circle. A circle is the locus of points equidistant from a given point. And we'll talk the conic sections. All the conic sections we'll talk about a definition that has to do with this idea of a locus. A locus is just a set of points that share some property. So the circle, the set of points is the set of all points equidistant from a given point. So that's the property they share. They're equidistant from the given point. So the way that we usually see this is all points the same distance from, and what is this given point that they're all equidistant from? What part of the circle would that be? What is it? The center. It's going to be the center point. So we have all points that are the same distance from the center. And what is that distance going to be? What part of the circle is the distance? The radius. That distance is the radius. And if we go back to this picture, our circle is on the cone. The center of the circle is the axis of the cone, and the distance is the distance from the axis of the cone to the cone itself at that particular location. So that's what we're talking about. When we're dealing with circles, when we're dealing with conic sections, this idea of distance comes up a lot. So let's remember what the distance formula is. What is the distance formula? Distance equals, I'll get us started, square root. Remember what we do for the distance formula? Anyone? All this is, I'm just going to write it in a different order. y1 minus y2 squared, and x1 minus x2 squared, and we're adding those together. So that's our distance formula. The distance between 2 points, x1, y1, and x2, y2. That comes up a lot when we're dealing with conic sections. So what we're going to do is our distance is our radius, and our center is our given point. So when we're dealing with conic sections, we'll use this point HK for a lot of things. So our center is HK, our radius equals R. We can plug these numbers into the distance formula and come up with the equation for a circle. So our standard equation for a circle is x minus h squared plus y minus k squared, and this should be familiar, I hope, equals r squared. So rather than putting the square root, we're just squaring both sides. So that's our standard equation of a circle, with the center at the point hk and radius r. And a couple things to remember. Notice that the sign, here we have x minus h, and here we have positive h, so the signs change when we put them between the equation and our point. And in our equation, our radius is squared. And before I go on, I wanted to ask one more question about the distance formula. Why does the distance formula look like that? Where does it come from? It's the Pythagorean theorem. The distance formula is the Pythagorean theorem. The distance formula works because the Pythagorean theorem is true. That's why the distance formula looks like this. These are two sides of a triangle, and this distance is the hypotenuse of the triangle. So that's why the distance formula looks like it does, because of the Pythagorean theorem. All right, if our center of our circle is at the origin, what does our equation become? If h and k are 0, 0, our equation turns into x squared plus y squared equals r squared. We have this nice, easy formula if our center is at 0, 0. Is everybody good with our equation of a circle, how we're defining it, and the idea that it's a simple piece of a cone, curve traced out on a cone? All right, so what I want to do, I just want to go through a few examples of the kinds of problems that you might be asked to solve that have to do with circles, just so we can think about circles using this equation. Shouldn't be too complicated, nothing really entirely new today. All right. Start with an easy one first. Let's say we want to find the equation of a circle that our center is -1, -4, and it contains the point uh, 5, 7. So we know our center, it contains this point 5, 7. So what do we need to find here to write our equation? We need to find our radius. So really what this equation is asking us is find the radius. How do we find the radius? What do? So we're going to plug our points, basically plug them into the distance formula, right? Distance from the center to the point is the radius. So let's plug in our points. So our radius is going to be the square root, and I'm going to plug them in. I'll say 5 minus negative 1 squared plus 7 minus negative 4 squared. One more parentheses there. So 5 minus negative 1 squared is 6 squared, we get 36. And 7 minus negative 4 squared is 11 squared, and we get 121. You guys know the trick for multiplying numbers by 11? Did I talk about that one before? So if I want to multiply 23, it's kind of a sidetrack here, times 11. Take these two numbers and separate them, and then add them together. So 45 times 11 is 5, add those together, 495. And if we end up with a number bigger than 10, then we carry the 1 over to here. So if we had, say, 67 times 11, so we'd separate those, 6 and 7. 6 plus 7 is 13. So I put a 3 there, carry the 1, and that would be 737. Kind of a cool little thing. Anyway. And I talked really quickly about that, the powers of 11 in Pascal's triangle. So that kind of happens in Pascal's triangle also. Anyway, back to the circle. 36 plus 121 is, so we get the square root of 157. So our equation of our circle is going to be x minus negative 1, so x plus 1 squared plus y plus 4 squared equals 157. That would be our equation of our circle. A pretty easy problem there. Questions? All right, let's do a slightly different kind of problem. Let's say we want, for this one, we're given the endpoints of a diameter. Our endpoints are 3, 4, and negative 5, negative 6. We want the equation of the circle. So what do we need to do here? We don't have the center or the radius. We need to find both. How can we find the center and the radius? Okay, so we can find the center by finding the midpoint of the diameter. The center is in the middle of the diameter. So our center is the midpoint of the diameter. And what Simone said is once we find the center, The radius is the distance from the center to one of these points. That would give us our radius. Is there another way we can find the radius? Half the diameter. So we can find the distance between these 2 points and divide by 2. So either way works. So let's do the first suggestion we have. The center is the midpoint of the diameter. How do we find the midpoint? How do we find the midpoint between 2 points? What's that? We could use the distance formula, but there's a nice easy way to do it. x1 plus x2 divided by 2. We find the average of the x values and the average of the y values. So our center is going to be at 3 plus negative 5 divided by 2. That's going to give us our x coordinate. And 4 plus negative 6 divided by 2. So we're finding the average of the 2 points. So 3 plus negative 5, what do we get? Negative 2 divided by 2. We get a negative 1. And 4 plus negative 6 is negative 2 again. So we get the center is at negative 1, negative 1. And then we can find the distance from the center to either one of these points. So our radius is going to be the square root, and I'll just use this point. 3 minus negative 1 is 4. Squared, we get 16. And 4 minus negative 1 is 5. We get, square that, and we get 25. So we get the square root of 41. So our equation is going to be x plus 1 squared plus y plus 1 squared equals the radius squared equals 41. Circles are nice. A lot of times in math we try to turn a complicated problem into a problem involving circles, and then a lot of times circle problems turn out to be problems involving triangles, because we can make, when we did trigonometry, that was all turning circle problems into triangle problems. So circles and triangles are our two friendliest shapes in math. Alright, let's look at another kind of problem. I think you guys will really like this one. This will bring back good memories. Alright, let's find the equation we want the standard equation of the circle, and here's my equation of a circle not in standard form. So we want the standard equation of this circle. What do we have to do here? Any ideas? Factor it involves factoring. It's related to factoring. We want, so remember our standard equation of our circle has x minus something squared and y minus something squared. So we need to get this, somehow get this into the form where we have x minus something squared and y minus something squared. Do you remember a process that lets us do that? Group the x's together, group the y's together. That's a good first start. So I'm going to write this as 9x squared plus 54x, and I'll put some parentheses here, plus 9y squared minus 36y. And I'm going to put the 17 on the other side, so equals negative 17, because we need our radius squared over here. We can divide by 9. could do that. Let's do one other thing first. What do we do here? Complete the square. Twice. Once for the x and once for the y. So we were hoping that we'd never have to do that again, and now we get to do it twice in one problem. On a Friday. Isn't everybody excited? All right, so now what I'm going to do to complete the square. So we're going to complete the square in each one of these parentheses. We're going to complete the square for the x, complete the square for the y. So to complete the square, remember when we have a leading coefficient here in front of the x squared, I'm going to factor that out. So I'm going to write a 9 x squared plus 6x and plus a 9 y squared minus 36y. And we are going to divide by 9, but I want to wait until the very end to do that, Joanne. Or we'll divide by 9, I want to wait until the end. Because our arithmetic turns out nicer if we divide by 9 at the end. So I'm going to complete the square. 9x squared. We divide this number in front of the x by 2. So plus 6x. And we divide that by 2 and square it. So 6 over 2 is 3 squared, and we add the 9. Plus 9 y squared minus, and I forgot when I divide by, when I factor out the 9, I get a 4y. 4 divided by, negative 4 divided by 2 is negative 2 squared, which is 4, equals minus 17. Well, what do I have to do when I complete the square? I added some stuff to this side of the equation. I have to add to the other side of the equation, so I still have an equation. And what I have to be careful of is this 9 is multiplying that 9 is multiplying that 4. So what I added to this side of the equation is 81 here, and I added a 36 here. So I need to add a plus 81 on this side and a plus 36 on that side. And now each of these parentheses is a perfect square. So I get 9x plus 3 squared plus 9y minus 2 squared equals, and we add all these together and we get 100. So I'm going to say x plus 3 squared, divide by 9 now, plus y minus 2 squared equals 100 ninths. So I have a circle with center negative 3, 2, and radius 10 thirds. I love these kind of problems. You'll see these problems, this type of problem, a fair amount in this chapter. We'll do it with parabolas, we'll do it with ellipses, and we'll do it with hyperbolas as well. Questions on that example? Okay. Complete the square. Did you think you would ever see that again? All right, last example. Find the x and y intercepts. Of this circle, x minus 5 squared plus y plus 2 squared equals 21. All right. Hopefully we've gotten this down now. When we did this way back at the beginning of the year in chapter 2, we sometimes struggle with this. How do we find an x-intercept? Zero for y. At the x-intercept is where it crosses the x-axis, so y equals 0. So we knew it had something to do with 0, right? Y equals 0. The y-intercepts. How do we find the y-intercept? X equals 0. All right. So we plug those into our equation. Plug in y equals 0. X-intercept, so we get x minus 5 squared plus 0 plus 2 squared plus 4 equals 21. So x minus 5 squared equals 17. Take the square root of both sides. X minus 5 equals, when I take the square root, what do I need to do? Plus or minus. I heard somebody say it. Plus or minus square root of 17. So x equals 5 plus or minus square root of 17. So this circle has two x-intercepts. Let's plug in x equals 0, find our y-intercepts. So I get negative 5 squared, so 25, plus y plus 2 squared equals 21. Subtract 25, so I get y plus 2 squared equals negative 4. What does that tell us? It's an imaginary number, so no y-intercepts. So our x-intercepts are 5 plus or minus square root of 17, and the circle has no y-intercept. So a circle could have two x-intercepts and two y-intercepts. Could have no y-intercepts, two x-intercepts. Could have one single intercept if it's just tangent to the one of the coordinate axes at a single point. Or it could have no intercepts at all. All right, questions about circles? Other than why are they so nice? All right. Whoa. One more. Let's see. 12, 13, 16. 17, and then 19 through 41 every three. All right, there we go.